Today we will cover quantum optics. Like I said, we'll do 2 labs alternatively so that people in different labs can all benefit from the lecture. Our topic today will be on coherence, all right? And as a tool, we'll introduce correlation. Right? Coherence and correlations are basically the same idea, different phrase used by different communities. Coherence is used by physicists. It's used mostly in physics. Okay? And correlation is sort of mixed, but it's mostly in mathematics. And in some occasions, also physics. There's another word that has the same meaning, that carries the same meaning. It's called convolution. Convolution. Okay? So you probably heard of a convolution integral. Okay, this is used, I think, primarily in mathematics. All right. I want you to know that these 3 things are all the same. Okay? So this is the physics, a concept, a cook-up, a make-up word in physics as to represent a physics concept, and a mathematical representation of that is the same as correlation and convolution. Okay. All right. So to start our discussion today, I want to review 2 light sources that you use in the lab. Oh man, this is bad. Light source. This is bad too. There are 2 light sources in your lab. One is, of course, laser. For those of you who have not been who have not worked in the optics lab, you should know that there are 2 light sources that we use. One is blue, and the other is red. Okay, red is for alignment, and blue is the main laser we use for the experiment. Okay, so there's laser and there's LED. Okay, there's a red light LED used for aligning the microscope interferometer. LED is short for light emitting diode, and that is the thing that is on your phone. This is LED. Okay, the light that we have in this classroom is also LED. Okay, so we use both the light sources in the lab. LED and laser. Oh, this is better. Light source. Okay, great. All right. Laser is an acronym. Do you know what it stands for?
Light amplification by simulated emission of radiation.
Good. Very good. Light amplification. Light amplification. I'm sure everybody heard of this, but just to have memorized the exact spelling of this 5-letter might be challenging. Amplification by stimulated emission of radiation. All right, so that's what laser stands for. Okay, so it's an acronym for this. And this is, of course, light emitting diode. All right. So at the fundamental level, so say, let's just compare the red light LED and the red light laser. So let's say we have something at 635 nanometer. And for LED, we're comparing with, concerning with the red, okay. So fundamentally, they are both red, right? The photon color is red. So what really makes the distinction between these two sources?
Laser only has one frequency, LED has a range of frequencies.
That's correct. So this has bandwidth. So he's talking about bandwidth. Like here, I can specify the frequency, but here I can only say red, right? So there is bandwidth. Okay.
Laser is highly directional. LED disperse.
Okay. So directionality. What else?
Say coherence in the laser.
Ooh, coherence. Pretty good. What else? Anything else?
Process of production of light is different.
Generation process, right? Yes. What else? Anything else? Anything you can think of phenomenologically?
Power required.
Power. You mean like the emitting power?
Or the pumping power.
Pumping power. Okay. Okay, like efficiency to like input output power ratio, right? Yeah, I would say. Yeah, I would say power efficiency, or this is a more engineering point of view. Yeah, or I would say this is like the input output power. To be more precise, this is what you mean, right? Input output power ratio. If you want to have, say, 10 milliwatt output, how much electrical power you need to put in, right? Is that what you mean?
So I think basically LED just input electricity and light and just light come out, but the pumping there is a broader spectrum and oscillate inside inside a chamber or something, and output a single wavelength. So there's more power lost during that.
More power lost.
During the laser generation.
Oh, I see.
But also you can have high intensity lasers, but increasing the power of the LED will like make it explode, not like make it more intense.
Okay, cool. Great. Those are all valid observation, and that's the engineering aspect of the two devices. Yeah, but I would say, do you agree that all these characteristics are all linked together? Do you agree? What do you think, Phoenix? Do you think all of them are linked together? Yeah, it looks like very different characteristics. But are they separate concepts or are they linked?
Somewhat linked.
Okay.
I don't know.
I would say they are linked. But in order to see that connection, you really need to have a comprehensive view of how light are generated. And if we start from the source, it'll be easier for us to understand the differences. Okay. So let's start with the source. For LED, how is light generated? Well, basically just a circuit with a diode, a light emitting diode here, right? And when we run current through it, that excites stuff here, and light comes out. Pretty simple. It's very similar to the light bulb people use in the old days. You run electricity through a hot wire, and that tungsten wire get heated, and then it starts to emit light. All right. This is more or less the same process, I would say. Of course, here you have not the hot wire, you have a semiconductor, and a carrier is excited from the valence band to the continuous band, and then when it falls, it fluoresces, right? But I would say that's, in my book, that's pretty similar to light bulb. You heat the wire, and the wire release energy in the form of radiation. Okay. And so this is a pretty simple device. And the laser, the structure of lasers is more sophisticated. Right. I mean, at the fundamental level, they are all photons. Yeah. If you're able to take one photon, hypothetically, if you're able to take one photon from the LED, and you take another photon from laser, you won't see any difference. It's just like electron. You take one electron from this element, carbon, and the other electron from, say, hydrogen, and you compare them, there are no difference. Yeah. So fundamentally, at the fundamental level, there's no difference in the photon.
I mean, the energy level is different.
No, if you take the same frequency, if you take identical, if you take the same photon, right? Fundamentally, they are not different. Okay. But what really makes the difference is in the generation process. Okay. So let's see how this goes. Okay. So laser, like LED, also start with a lot of laser nowadays start with also an LED as its core component. You also run a current through it, right? And in doing that, light are emitted. Yes. So far, identical with LED because this is just an LED. But what makes the laser different is this structure called cavity that surrounds the LED. Okay. Cavity is basically two highly reflective mirrors. Usually they comes in pairs. One is really high, so reflectivity could reach 99.9% in the desired bandwidth range. And the other one, still high, but relatively low compared to this. So maybe like 90%, all right? So you take two mirrors, one is really high and the other is not as high, but still high. And you sandwich them. Not literally, but you sandwich them around this laser dial. And you have a cavity. And what is a cavity? Cavity is a light trap. Yeah? Okay, cavity is a light trap. How so? Well, first of all, we notice that this is just very highly reflective mirror. So if I have a photon that is generated, say, You just represent a photon by a circle that is generated in this fluorescence, and the photon flies to this mirror. What's most likely to happen is that it will bounce back, right? Yeah, there's only one photon, so it either bounce back or transmit. There's a 90% chance for it to bounce back. That's what reflectivity means. The probability of a photon to go through or reflect. Right? So you'll bounce back on the encounter of this mirror. And when you reach the other mirror, you'll also bounce back because the reflectivity is so high. Yeah? So bouncing back and forth makes this photon trapped in this space. All right, so that's the first order approximation of what cavity is. And of course, there's resonance structures and all that. Okay, but we won't bother with that. But that just said it is a light trap because we have two highly reflective mirrors, and that just kind of boxed these photons in this space. Okay, so very simple. Okay. Now, why do we want to do this? Why do we want to put a cavity around the light emitting diode? Well, because as we discussed last time, there are two types of particles. One is lion and the other is sheep. Were you there? Yeah. Were you in the last lecture?
I watched it.
Oh, you did? Okay. So you watch it. All right, good. So I can ask you questions. So it's fermion and boson, right? Which one is lion?
Which one is lion?
Yeah, which one is lion? Lions like to stay alone. They don't want to. Fermion.
But the spin is, I only know one has a spin.
Okay. So just a little recap. Fermion, they are lions. They like to by themselves. They like to be alone. Okay? Boson, they are sheep. They like to group. They like to mimic each other. They like to stick together. Okay?
Sorry.
That's all right. So we know that matters such as electrons, neutrons, protons. Matter can be either fermion or boson, okay, depending on the spin characteristics, depending on its spin composition. But photon, pure energy, photon is boson. Okay? So one of the things that boson does is when it sees one sheep, the other sheep will follow the same direction. When it sees one sheep going there, the other sheep will follow that direction. So that's why we want to keep this first photon, this first photon trapped around the diode, because every passage it has through the diode, it will trigger the next emitted photon to follow its direction. Okay? So when you go through this, there's another photon generated. If it happened that another photon is generated, it will follow this direction. And on this passage, if there's another photon, so there are two now. If on the second passage, if there's another photon generated, it will follow this direction. So there are three now. All right. So they start to become a team. They will mimic each other. Technically, these are called, they occupy the same mode. The mode is described primarily by three numbers: frequency, momentum, okay, K, and polarization, I call S. Frequency, momentum, and polarization. This is like the identifier mode. Mode is an identifier for photons. It's like your national security. It's like your social security number. Everybody has one number. Every photon has a mode that is that describe this photon. Okay, and what boson like to do is that when there is a photon in this mode, other photon that is generated have a high likelihood to be generated in the same mode. Okay, so when I say they travel in the same direction, that means they have the same K. Okay, all right. So the first one is in this mode. Once this happens, the second and the third and the fourth, they all get pulled into this same mode. Later, when we talk about quantization of fields, we will have a more quantitative discussion on what mode is in terms of field. But right now, I just take it as an identifier, a tag, and when photons like to have the same tag with the same tag. Okay. All right. So the purpose of having the cavity is to have this first photons to pass through the LED multiple times so that everybody can fall into the same mode. Now, what happened is after there are so many of them, you start to have some emission, right? Because this is 90%. I mean, this is only 0.1% chance of getting transmission, but this is 90%. So photons are more likely to leak out from this end. And when there are enough of them, the number of photons leaking out become observable. And by that time, if you have like, say, 1 milliwatt leak out, how much power do you have inside? 1.1?
90%.
1?
Oh, 10.
You should have 10, right? You should have 10. You see? So you start to have, this is called lasing. You start to have lasing when you already have a lot of them inside. Yeah? And when there's a lot of them, you can you can be assured that all of them follow the same, they follow the same direction, they have the same mode. Okay? That's why in the laser, you have a very narrow bandwidth in the frequency. Very narrow. Yeah? And also, you have a very narrow momentum spectrum. Let me just use K or Kx. Okay, so let's assume it's one-dimensional. K in, okay, let me just use Kx to indicate the transverse, this outer plane, because the in this, okay, let me use this of Kx. Kx is in this direction, and this is Kz. Okay, and K. Yeah. All right. So I'm gonna just use Kx because it's simpler. So you will also have very narrow distribution in Kx because they all want to be the same, right? So again, very narrow distribution. Yeah. Okay, so this too, there's one more thing.
So the top is this. I really recognize this direction. Yeah.
Oh, sorry. This is a KX. It is transverse to the propagation direction.
So it's only the z-axis.
Yeah, KZ. Oh, let me just write X and Z. Easier. X and Z. Okay? Yeah. There's one more thing. What I drew here is the power spectrum. Power spectrum. Anybody has any idea what I'm talking about? Power spectrum versus just Fourier spectrum.
Well, for photon is the same, no? Because the frequency is the energy.
Okay. All right, so this is basically just a mathematical term, okay? Fourier transform. All right, so just a little, so this is just something on the side. So Fourier transform. When you have a function, let me just use time. When you have a function that is transformed to a Fourier spectrum, yeah, you will have an amplitude, and you will have a phase. Get it? Okay, this amplitude, let's just call it S. This amplitude is called power spectrum as a function of frequency. The amplitude as a function of frequency, that's called power spectrum. This is what you measure in your spectrometer, okay? This is power spectrum, okay? And this is this phase. The phase of each frequency component is also different. The phase as a function of frequency is called phase spectrum. All right, so this is a mathematical terminology. Yeah. Most of the time, majority of the time, when we talk about bandwidth, when we talk about spectrum, we're talking about power spectrum. Okay. But you should know that there is also phase spectrum that is very, very important. And as a matter of fact, it plays a key role in today's discussion. All right, so I would say to fully understand the spatial and temporal distribution, we need to know both phase spectrum and power spectrum. Okay. For laser, of course, it takes only values in this very narrow range. Yeah. So you won't have any value outside of that range. Let me just put S here and put Y here. And this is okay. The phase is uniform. Okay. And if it's not uniform, it's likely linear. It has a very well defined shape. It's not random as compared to random. Okay. So when you have so these are the spectral characteristic of the photon emitted on the laser, all because of this grouping characteristic of boson, all because of that property. And that gives us a rather monotonic oscillation in both space and time. Okay, so everything is very, very regular. Looks nice. But for LED, if we compare, so let me say this is laser. Laser. This is a laser. Okay. For LED, what do you think, David? It's really broad, right? This is LED. Yeah? How about phase?
Also Gaussian.
Huh?
Also Gaussian.
No? You'll be like, this. It's kind of random. Yeah? What about K? This is also power spectrum. It could have this shape or that shape or this shape. It could have like many different shapes. Yeah? But one thing that we know for sure is it's gonna be broad. Yes? Because we know light coming out of LED goes in all directions. Okay. Now, so this is what happens when the emission is independent. Everybody's doing their own thing. When energy is thrown into the light field, it can occupy this frequency, this frequency, this frequency, this frequency. It doesn't matter. You just go like, and they are all emitted at different time. One is this time, one is that time. So they have an initial phase offset, and that offset is kind of random. Yeah. And the direction also emit there, everywhere. Okay. By the way, this is 0. Okay, so this is positive direction. This is negative direction. Positive, negative. Yep. Okay. All right, let me just erase this.
Where does polarization come into this? Is it the base?
Oh no, polarization is, sorry. Yeah, that's a good question. So far, I have not specified polarization. Of course, if I would draw polarization, okay, so let's say we divide polarization as vertical and horizontal. Okay, so this is vertical, this is horizontal. Yeah. For laser, of course, everything will be the same. So it's either all vertical or all horizontal. Okay, so let's say it's this. Okay, and this is a delta function. So very small distribution. And for LED, is again everywhere. Right. So this is the difference between. So you see the clear difference between correlated emission. This is correlated emission. Everybody is watching everybody, and they all try to do things in a collaborative way. But here, the emission is independent. Okay, nobody talks to anybody. They just go like, right? Because when the first photon, even though photons are boson, there's no use of it, of this property, if the boson is long gone. If the first boson is long gone, photon is long gone when the second photon is generated. So they all generate at different time, and therefore they really have no chance to interact with each other. Okay, so this, of course, this grouping at the microscopic levels, it still take interactions. It still take interaction for this grouping to occur. And that interaction is the photon need to interact with the photon light emitting diode. Okay, this light matter interaction needs to occur in order for the grouping to facilitate this grouping. Okay, so if the photon is long gone, then there's no chance for this interaction to happen, and therefore no grouping. And that's why the emission is independent, uncorrelated. Yep. Now, so these are the spectral property of the two light sources. If we will plot out the wave field, okay, from here and from here, what will we see? For a very narrow distribution, it looks like this. So this is a laser. So this is both in. This could be space, or this could be time. Okay, so all very regular. So this is a laser. Because we know a very narrow distribution in the Fourier spectrum is a sinusoidal wave, right? So they are very regular. It's not hard to understand from a mathematical point of view. Now, for this LED, it is a little harder to understand, to visualize what it will look like. Anybody has any idea?
Just a lot of frequency times a but it still has a periodic nature, but each period is much more.
Okay. Yeah, it's close. What do you think?
I would guess it's a straight line to say,
Straight line?
average it out to one column.
Okay.
It will be inside a bandwidth.
Uh-huh. It'll be what?
Inside a bandwidth, like all the values inside. You have like two sinusoidal inside that area. So
they will oscillate between two values.
No, inside any region inside. Means different rays will be in different.
I don't get it. You want to draw it?
Something like.
You can draw here. I have a little space.
Something like. Like
it wobbles?
Frequency inside this different.
Okay. It's called modulation.
Yeah.
Yeah, thanks. Thank you. Correct. Yes, he's right. Let me use this. He's actually right. The main difference, so even though they are centered at the same frequency, because the phase spectrum, one is very regular and the other is random. That means, so imagine we have a lot of wave. Let's just say, even for this small region of components. Okay, so let's take this component out, and along with their phase, and let's try to plot it and compare with laser and see how they are different. Okay, So for this so let's say there are three frequency components in this in this small interval, and so you can imagine that there are three waves that are very similar in periodicity, okay, but they are offset by a little bit. Some or see they are offset. Yeah, they are offset relative to each other. Okay, and as a consequence of that, in some places the wave will constructively interfere, and in some places they are not all of them will do the same thing, but the majority, so like two of them will constructively interfere, or two of them will destructively interfere, right? So in some places you have constructive interference dominating, and in some places you have destructive interference dominating, right? If you have, so say here we have the mostly line up, right? So we have constructive interference dominating, okay? And here these two are opposites to each other, so we have destructive interference dominating. So the result of that is the amplitude here will be high, and the amplitude here will be low. All right, in the resulting waveform. Okay, so the result is this. We'll have a modulation. We will have an irregular, slow modulation in the amplitude. But inside, so this is called envelope. And inside this oscillation, we call it carrier. The carrier will still be pretty regular in terms of periodicity. Okay, and that's which is centered at omega 0. But this envelope, so this is 1 over omega 0. Okay, still, so that is the same as the laser, 1 omega 0. But the amplitude is very different. Here the amplitude is constant. But for LED we have modulations. Okay, and this is both in space and in time. Yeah, because as you can imagine, I have also phase spectrum for my spatial frequency, and for LED is also random, and for light is uniform. Okay, so this works. The same Fourier transform works in both space and time. Now, although this looks very irregular, there's still a small degree of order in it, and that is, besides that this carrier oscillation is at the same frequency as this light, this bump, okay, the width of this bump is have a period that is characterized by the, so if I just take this, let me just call it omega prime. Okay, that is characterized by the width, of your frequency components. Okay, so during this time you have almost a constant amplitude. I'm exaggerating right now here, but during this time you have, it's almost like you can group this into different sections, and each section give you like a wobbly pattern like this, and sometimes this section will dominate, and it will oscillate in a constant amplitude and at this frequency, and sometimes the other section will dominate, and for that period of time it will oscillate in so like this section versus this section. In that time, it will oscillate at different frequency and at constant amplitude. Okay, so within this time, it will behave as almost as a monochromatic wave. Yeah. This time period is called coherence time, or more precisely, optical coherence time. Yeah. And in space, it's the same thing too. Okay. In space, it goes like this, and it also have wobbles. In a certain area, it has a constant amplitude with a very regular oscillation, characterized by certain k. Okay, maybe so like this by a certain k. And so for these areas, if you take points from this wavelet in this area, the oscillation of the field will appear very regular in this area. But when you move to another area, it's a different story. They will oscillate in another spatial frequency with a constant amplitude. Okay. Okay. So the same story goes for both time and space. For time, it's called this window. This time window is called coherence time. For space, this area or this length is called coherence length. Okay. So for time, it's coherence time. And for area, it's called coherence length. And of course, to be more precise, you can call it optical coherence length, or even more precise, optical transverse coherence width. Okay. Sorry, let me just call it coherence width, because sometimes people use the longitudinal. Sometimes people call the coherence width in the longitudinal direction where the light propagate the coherence length. So let me just call it transverse coherence width. Okay, coherence width. Okay. All right. So now, having given account of their spectral properties, we know that they have the so-called coherence characteristics are determined by their spectral property, right? And also directionality, right? Because if you have a narrow distribution in the transverse momentum close to zero, that means you're not going everywhere. You're going pretty much forward. That's very directional. For LED, it's not the case. Okay, so we can see this also from the spectrum. Yeah, bandwidth, of course. We already talked about one has a broad bandwidth and the other has a narrow bandwidth because of this bosonic property of photon. Generation process, yes, both are generated by LED, but the other one has a cavity structure around it, and that makes all the differences. Okay. Power efficiency. Okay. Now, this conversion, I'm just gonna talk about output and input power ratio. Okay, there is a certain ratio in the conversion, right? A lot of them are wasted in the heat. Okay, but certain ratio, certain energy get absorbed by the charge carrier, and the charge carrier make transitions in the band gap, and that emits light. Okay, so those are converted to light. For this is the same thing. Okay, it's the same thing. However, this energy for LED is distributed over all different frequency components. So the spectral intensity, if you have a filter, right, and you just take a slice of this spectrum out and you measure its power, you find that it is not very high, it is low. Okay, and also the average power, because it's distributed, so the average power is also low. Yeah. So low average power. Okay. But for laser, because all the energies are dumped to the same mode, right? So the spectral power is very high. And since you only have since you only have photons of this kind, all the light you get, I mean, all the total energy that is in this area is concentrated here in a very sharp, very narrow spectral range. Okay, so maybe let me just say low spectral power. And this is high spectral power. And since your spectral width is narrow, this is equal to high total power, because you have a very narrow spectral width, right? So is it easy to generate a 1 watt laser beam? Well, it's not too hard. Okay, is it easy to generate a 1 watt LED light? Oh man, the energy consumption is going to be very, very high. You see what I'm saying? Okay, so if you want to make a light sword, like in the Star Wars, if you want to make a light sword, you want to use a laser, not LED. Yeah. Okay. So this is also has to do with this spectrum. So you see, all of them are related. Okay. Now, okay, I think this is a good time to take a break. All right, so let's take a 5-minute break and then we'll come back for our discussions on correlation. We haven't get to that yet.
I have a question.
Yeah.
About how we generalize to the continuous interval for the LED power spectrum. Now we have the modulation path. But what if we had a uniform distribution in the power spectrum? Would it then be a signal?
If we have a uniform distribution on the power spectrum,
yeah,
and then
would we then see a modulation wave, or would it just be a constant power across time and space?
That has to do also with the phase.
Yeah.
If your phase is constant,
yeah.
So it's basically, here we have a combination of narrow, broad, right?
Mm-hmm.
You're asking about narrow, broad.
Yeah.
Broad but regular. Yeah? That is what a frequency cone is. Frequency cone.
Okay.
Yeah. Frequency cone. That's a special type of laser. It's a very regular pulse train. With all the carrier. Where's my black? See, I have difficulty finding pens. Where's black? Okay. Okay, let me use. Oh, here. It's hiding here.
Hiding.
Okay. They have regular spacing, very regular spacing, and also the carrier envelope phase is the same for each pulse. So the carrier always have, in this case, the carrier always have its top lying with the maximum of the envelope.
I buy a larger one.
Okay.
To
So that's what
use the
frequency
simple
comb
everything.
is. Frequency laser comb. Okay, so that's what happens if you have a broad spectrum and regular phase spectrum.
Okay, interesting.
Yeah, and this is very cool stuff. This is in the realm of ultra-fast optics. Very important tool. People get Nobel Prize for it, for making this light source, and it is also a very important tool for atomic clock. Yeah. So very cool stuff. Okay.
Yeah, interesting. Thanks.
Phoenix, are you going to stay or are you not sure yet? It's okay if you still need time to decide. I just need to know because there are 4 people who has dropped, and I need to rearrange the groups. Yeah, so I kind of it'd be good if I can know your decision. Not it doesn't matter today. I'm just wondering. Do you think you will stay, or do you think you still need time to decide? Huh? You think you stay? Okay. If you will stay, remember to send me which evaluation track you would like to take. You prefer to take theory track or experiment. Send me an email, please. Okay. All right. Okay, so guys, let's get back to our lecture. So we see that from our earlier discussion, we see that all these properties are kind of straightforward. Okay, but coherence took a little time to explain, right? Now we will zoom into this property because that's the main topic of today's discussion, coherence. All right. So phenomenologically, how do we tell? I mean, of course, bandwidth. Yeah, of course, we can use some kind of spectrometer to measure it. You can see that directionality. Yeah, focusing, divergent versus collimated, right? Coherence, generation process. Like this, we can see. This we can just measure power. Generation process. I don't know. You have to open up the laser in order to see the cavity. But how do we see coherence? How do we see they are different in coherence?
Can we use it in interferometer?
Oh yeah, that's a good idea. Interferometer. Okay, so let's see how that works. Okay, good. Let's erase this.
So is the bandwidth and directionality part of the coherence as well?
Yes. I mean, because they are all related to the spectrum property.
One is the time domain, and one is the space domain. No. Coherence, like I said, coherence.
Going in same direction, right?
There is spatial coherence and there's temporal coherence, right? And the spatial coherence is characterized by the coherence, transverse coherence width, and the temporal coherence is characterized by a coherence time. So coherence pertains to both spatial and temporal. Yeah. So yeah, that's the point of this discussion now. We want to see like where does this show phenomenologically. So if we have not have this discussion, how do you know that they are different? The two light sources are different in coherence. Like what is coherence actually? Who come up with that word? Yeah, it's not in my high school dictionary. It's not in my English class. Okay, so how do you know? Well, someone suggests that how about we set up an interferometer? That's a good idea in my opinion. So let's do that. We have an LED. An LED emit light rays in a lot of directions, right? It doesn't matter. We could use a little hole, a pinhole to make it less divergent. Yeah. We can even use two pinhole to make it almost look like a beam. Oh, no, okay, let me not do that. All right, let me not complicate. I'm sorry. Let me not complicate this. Let's just take this beam, this cone, and then let's take a big mirror. Yeah. Let's take a big, sorry, not big mirror, big beam splitter. And part of it, a 50-50 beam splitter will make part of it transmit and the other part reflect. Yeah. And then I'll take two mirrors. This is a mirror. This is a mirror. Okay. And this will go like this. This will go like this. Yeah. The drawing is not very pleasant. This is because it's divergent. But you get the idea. Now take a beam splitter. Right? Okay, let's focus on this part. Of course, there is also this part. But let's focus on this part. So for these guys, let me just use red. Red. So they go like this. And I'll use blue for beam coming from the top. So they go like this. Yeah? Okay. And we have a camera. We set up a little camera here. And we want to see its image. What will we see on the camera? So for LED. So this is the camera screen. Well, there are arm BA and arm B. Yes, this is one arm. This is one arm. This is A. Okay. And this is the other arm, the second arm. This is arm B. Yeah. So if I have a piece of paper and I block arm B, what do I see on my camera screen? I will see an image of arm A. Yeah. And it's basically a bomb. Okay, a bomb, a cone. Okay, now if I block A and I let through arm B, what do I see? I see also a bomb. They're identical. right? Now, if I let both go through, what do I see?
Probably the same.
A brighter bulb, just doubly bright. Okay? So the result is a brighter bulb. I'm just brighter bulb. Doubly bright. Yep. Now, if I would do the same thing with laser, okay? With laser, I have only one beam. And the beam is also split by the spin splitter, reflect by mirror, and again, it goes to the camera. Okay? And the other arm is the same thing. Bound by the mirror, split by the beam splitter, bound, reflect by the mirror, and split again by the beam splitter. Okay, so I have this 2, 1 and 2. So this is the laser. Yeah? What do I expect to see? Well, first of all, if I block on B, what do I expect to see on A? Huh? A point. That's very good. I will see a smaller, not exactly a point, but it will be much smaller than this bomb. Yeah? How about B? If I block A and I let through only B, then I'll see this. Okay? What if I let through both? What?
It depends upon the arm length, whether it's constructive or constructive at the end.
Okay. Generally, if you're not very careful, generally what you will see is just basically fringes, linear fringes like this. If you're very, very careful with your alignment, you see circular fringes. Okay? But let's not go into details here. Let's just take this for case. You see linear fringes. Yeah? So, you see, in one case, this structure is called an interferometer. Okay? To be precise, this is called a Mach-Zehnder interferometer. It is meter. It is similar to, its working concept is the same as the microsync interferometer that you're familiar with, except that here it uses 2 beam splitter instead of 1. In microsync interferometer, we have 2 mirrors and 1 beam splitter. In Mach-Zehnder interferometer, we have 2 beam splitter, 1 beam splitter more. That's all. Okay. All right. So when we pass the light from the 2 different light sources, through this interferometer, we see different results. One is just a brighter bulb, doubly bright, and the other is new structure, new fringe structure comes up, right? Okay, so they are qualitatively different. Apparently, something has happened between this, some kind of interaction is happening between these 2 beams, which give rise to this fringe structure. Okay. Now, if we will take a line cut, if we will take a line out. Okay, let me just call it this X. This X. If we will take a line out, the LED will look like a bulb. Yeah? And the laser, LED, the laser will look like this. All right. We call this interference. We call this interaction between the two being interference. Okay? And it is, so two being, so apparent that two being interact. Okay? And we call this interact interference. Yeah? And an interference, these fringes, so mathematically this shape, this intensity profile can be described as two terms. Yeah? And an interaction term. And that interaction term typically take a form of cosine K6. Yeah? So for LED, there's no interaction. There's no interaction. It's only these two terms. And for laser, there are three terms. There's two DC term and this AC term. So let me call it DC. Let me call this AC because this oscillate. Okay? So this is for the laser. Yeah? All right. So far, so good. Now, you'll be very surprised. All right. Let me just back off a little bit. So you see there are two different cases. Okay? There are two different cases. One without interaction and the other is with interaction. So for convenience, it'd be nice to describe everything under the same formula, right? So for convenience, we assign some kind of a parameter. Okay. One here represents first order, but it is immaterial right now. We assign a parameter to it, and if this parameter is 1, okay, then we have interaction, we have interference. And if this parameter is 0, we have no interaction, no coherence. No interference, right? This parameter is what we call coherence. Like this thing is called coherence. And 1 here indicates first order coherence. So if the first order coherence take a value of 1, then you have interaction. If first order coherence take the value of 0, you have no interaction. Pretty simple, right? In this case, coherence basically represent the ability to interfere. Coherence in this context characterized the ability to interfere. The ability to interfere or the ability to interact. Yeah? So if you take 1, then we have something called a full coherence or fully coherent. Let me just use an adjective. Fully coherent. If it's 0, it is incoherent. In means no, 0. All right. So far so good, and it's almost trivial to have an additional parameter to tell us something that easy. All right. Well, If you're surprised if I tell you that in this case, for the LED, it is possible to get fringes out of it. Okay? It is possible to get fringes out of it. All you need to do is a more detailed alignment in time and in space. Okay. But the fringe that you see from LED, even after like very intricate alignments, the best fringe you see will still be much less visible than this. Okay. The best you will see is probably something like this is laser. Let me use this. The best you will see is probably going to be something like this. Okay, you see that this does not reach zero. Or the dip does not reach zero. Yeah. So this is also LED. Okay. So the reason really that people define this additional parameter in front of this interaction term is to characterize this type of behavior. This is called partial coherent. Partially coherent. Okay, so they find that besides these two extreme cases, there are also a lot of things in the middle. Even for laser, sometimes you find that this does not go to zero. This probably will go to a low value, but not zero, like 5% or 10%. If this is 100%, you probably go to 5% or 10%. Yeah. So in order to describe this interference pattern that is, that kind of shows but not strong, I give a name called partially coherent, and they need this parameter to characterize it. Okay, so in light of this coherence parameter, we see that coherence is not a black and white thing, or interference is not a black and white thing. It has a continuous spectrum. It takes all different values from 0 to 1. And the difference between laser and LED, in view of this, is not qualitative, but it's quantitative. Okay, so in this continuous spectrum of 0, 1, right? This is LED. This is laser. Okay? That's all. It is a quantitative difference, not a qualitative difference. You can have ways in your measurement process. You can improve your setup so that you move LED up in terms of its coherence. It's possible. Okay, later we'll talk about how to do that. And you can also have a badly manufactured laser, and that is a little closer to the other end. It's all possible. Yeah. So coherence characterizes this continuous transition from 0, no ability to interfere, to fully capable of the interference. Okay.
Can also have fully coherent laser, right?
Sorry?
Can we also have fully coherent laser?
Yeah. Practically no. It's like 100%. No, you can approach it. Yeah. But yeah, you can get very, very high contrast. Yeah, like 99.9. Yeah.
Can I say a white light coherence is 0?
white light coherence is 0.
I say that.
No, because now we're gonna now we're gonna talk about how does the concept that we just discussed, coherence time and coherence transverse coherence width, relate to this concept, relate to this partial coherence. Okay, and for white light, it is the same. It is the same idea. This concept can be applied to white light. Okay. All right. Okay. So, like I mentioned that there are ways to make LED interfere, right? How so? Let me give you 2 examples, and this should suffice as an explanation of how coherence length and coherence width and coherence time relate to interference. Okay. Now, coherence time, like I said, coherence time are the intervals of that wobbly stuff that during which it has almost a constant amplitude and a well-defined oscillation. Yeah. Okay. So that's focus. So say it's like this. Okay. Let's focus on this bump. Okay. Yeah. So let's just pretend that it has one bump only, and that bump is like this wide. Yeah. So for LED, that bump has a very small, because remember this bump has the width of 1 over frequency, right? And for LED, the frequency width is pretty large. So this is a very narrow bump. Okay. It's not a pulse, but I'm just like also cutting this out for illustration purpose. Now, when you have it go through the interferometer, so yes, sorry, and yes. At the end, you will get two of them. That is slightly delayed, right? And this delay will have to do with the path length difference. Yeah. So if this is L1 and this is L2, then this is C L1 minus L2. Yeah, slightly delayed. Okay. Let's just do a little.
It should be divided or C over.
Hmm? Oh, I'm sorry. Thanks. Okay, thank you. All right. So that's let's do a little math here. Okay. What is a nominal value of this? Can we do an estimate? Let's say I know that the wavelength, it is red, right? I don't know how it is, like color is a continuous spectrum. Okay, so maybe if I go from, so I know 600 is red. Is 660 also red? Yes. Is 530 red? No. Right? Is 700 red? Yeah, red, but almost invisible. Yeah? All right, so you see, maybe in an interval of, I would say, 580 is probably red too, right? So in an interval of 80, I would say it's pretty much red. Okay, so let's just take a conservative estimate. Let's say our LED has a bandwidth of 15 nanometer. Okay, around at say 600. Yep. What's the frequency? What's the corresponding frequency width? Okay, so how do we cut? Does anybody know how to do this math?
2π divided by the wavelength.
Mm-hmm. And which wavelength? 600?
Yeah, the middle, right?
Huh?
The middle, right? 600.
600, okay. Then what? You're calculating a wave number. This is a wave number. I'm asking for a bandwidth in frequency.
All right.
Yes. Well, first we need to convert wavelength to frequency. How do we do that?
C by
Frequency and
C by lambda.
right? So this is velocity. Velocity times velocity divided by.
No, it's
It's lambda.
C continue, right?
Okay. So C lambda. Okay. Right. Good. So F is C over lambda. So here instead of 2 pi, let's replace this by C. Yeah? Okay. And we want to know the frequency difference. So if in wavelength we have 600 here and a width of 15 nanometer, then this must be 625 and this must be 537.75. Yeah? Correct? All right. So what we want to do is to convert this to frequency, and then calculate the frequency difference. And then we're done, right? Or, okay, let me just change my notation to mu 1, mu 2, delta nu. Okay. All right. So this is C nanometer minus C. Okay. You all have computers, so help me out. Okay, just crank this number out. 3 times 10 to the 8 divided by this minus that. Don't forget to put the nanometer unit in. How many hertz is this? Just give me an order of magnitude. Who has the answer? You have an answer? I'm waiting for you, man. You have the computer. All of you have computers.
575.
Yeah.
Okay. I get minus 1.391 times 10 to the power minus 1.
Minus 3.91 times 10 to the
power minus 4.
10 to the power minus 4.
Nanometers.
I think we changed.
Okay, let's do this. Okay. Okay. This is 30. And this is 50 over, right? Yes? Of course, minus, yeah. Because I should put this here. It doesn't matter. Let me just put a absolute value around it. Okay. So how come the frequency is so low? Oh, this is minus 9 in the denominator. So I should, instead of 30, I should have 3 times 10 to the 17. Correct? Okay. So this is 150 times 10 to the 17. Yeah? Now, since I only want an order of magnitude, right? So I don't need to bother with all this math. I can just put how many? So they are, so this is 1 point times 10 to the 2, and this is 6 times 10 to the 4th, yeah? 10 to the 17, yes? And so this is about 2 over 30. So this is about 2 over 30, and this is 19 minus 4, so this is 15. Okay? So the order of magnitude is 14. Yeah? Agree? Okay, so this is about 10 to the 14 hertz. Okay. Agree?
It's a lot.
Huh?
14 or 15.
14, 13, who cares? It's in that order of magnitude. Okay? Let me just go with 14. So that's this, delta mu. So that makes my coherence time how long? 1 over 10 to the 14. That means that's 10 femtosecond. Femtosecond is 10 to the minus 15, right? 10 femtosecond. Okay. So say if my path length differ by, say, 1 millimeter. Okay, that's pretty small for our optical alignment, right? So 1 millimeter by 1 millimeter divided by 3 times 10 to the 8, right? So this is 0.3 times 10 to the minus 11. 10 times 10, so that's 3 picosecond. 3 picosecond versus 10 femtosecond. Picosecond is 3 order magnitude. It's like kilometer and meter. So picosecond is 3 order of magnitude higher than femtosecond. Okay? So in other words, this differs by about 1,000 times. So this is really, really large. Super large, even for like 1 millimeter gap. If you make a mistake with 1 millimeter, you're missing by like 1,000. Okay? So you see, it's really hard. And so let's say, so if your difference is 1 millimeter, then that means this wobbly part, you break this chain to 2 parts, right? And the bump, so you have 2 copies of this, but this bump will be separate. Like the same bump will be separated by 3 picoseconds, while the bump itself is 10 femtosecond. You see? So that's why it's very, very difficult to make them interfere. But if somehow you're very meticulous and then you manage to align this within 1 micrometer, we drop by 3 order of magnitude down, right? So if we can manage this to drop this difference to 1 micron, then this will also drop by 1 micron. Yeah? So that becomes 3 femtosecond. Yes? So now, in that case, wow, it's pretty amazing. The 2 bumps will overlap partially. You have partial overlap. And for that period, for that interval of time, it can interfere. Okay? But that's how much effort you need to pay in order to make this interfere. Okay? So you'll see interference. And the more the overlap, the stronger the interference is. You can imagine if I have a little overlap like this, right? If I have a little overlap, then the interaction term is going to be, just working from this extreme, I have 0 overlap. If I have 0 overlap, I have 0 interference, right? So if I have a little overlap, I have a little bit interference. When I have a little bit interference, I have a little visibility. Okay, as my interference, my overlap increase, the interference can become bigger and bigger. Yeah. Okay, so that's how you make LED interfere. So it is possible, but just very difficult. Okay. So this is the first example. Coherence time. Concerning coherence time. If you can make them overlap within the coherence time, then you can have interference. So that's the meaning of coherence time. Overlap within coherence time, you can have interference. Now, next example. Okay, I think you might not be able to cover correlation today. That's all right. Next example. You take LED, and it's like this, right? So the example that we give are like on-axis. We take the on-axis spin, right? There's another detail that we need to take into account. Which is So we know spatially they are also very the field oscillation is only regular within a certain volume or a certain area, right? So what if your interferometer, like this arm, comes from, so I have, say, let me just draw a hypothetical wavefront, okay? A wavefront is defined by a constant phase, but here we don't have constant phase. But nevertheless, let me just draw this line, okay? Okay, so if my arm A, so this is arm A, this is arm B. If my arm A take the rate that goes through this position, okay? And my arm B end up, because you can trace back, you can trace the beam path back to its source, right? So say if my arm A comes from here and my arm B comes from here, they are not, ideally they should like overlap. They should be the same point, the same ray. But if it's not the same ray, can they still interfere? Yeah, that's the question. Okay, so this is the interferometer, and arm A just goes like this, and arm B just goes like this. Can they interfere if they are not the same point? Again, the answer is, if this separation is larger than the coherence, transverse coherence width, then there's no interference. Yeah. So I won't bother you with the calculation, but it carries the same idea. Okay. So so if this separation delta x is larger than let me just say coherence width. Okay, let me use W, coherence width. Then no interference. But if it is close enough, then yes. Okay. All right. So you probably heard of the double slit experiment, right? Double slit experiment does exactly this thing, right? We have a wavefront, hypothetical wavefront, and then we take 2 points. We have 2 pinholes. Let's select 2 points from this. So you can draw a line from the source to this pinhole, and that's one ray, and this is another ray. Okay. All right, but the ray doesn't matter. The spatial separation is what matters. Okay, so this is your source. Okay. And then at the screen, you will see interference pattern, right? Because the interference from the 2 sources, right? Now, if the source is a laser, you can do however, like whatever big whole separation you like. It doesn't matter. You're pretty much all, as long as it's within the beam, laser beam, it will always give you a nice interference, double slit diffraction pattern. But if it is sunlight or white light, yeah, sunlight, of course, different color will not interfere with red will now interfere with blue. Okay? So what happened with sunlight is if you put this close enough, for the red, it will have a periodicity, a certain periodicity for the red, as determined by its wavelength. For the blue, you will also have another periodicity. So you have two sets of interference fringes, one for the red and the other for the blue. Understand? But the prerequisite is that this needs to be close enough. Okay? And how close? Well, it is determined by the coherent, it transfers coherence of the sunlight. Can we theoretically know what this is? Very hard. Very hard. You have to go into the microscopic generation process in order to. Unlike the bandwidth in the temporal in the frequency spectrum is pretty straightforward to know. But the bandwidth in the momentum spectrum will have also something to do with the geometry of the source. Not just the generation process, also the geometry.
So to do with the what's called bin waste?
No, the bin waste is a consequence of this parameter. This is like a set parameter when the light is generated. Just like the bandwidth, it is a set parameter. Okay, it is determined, the frequency bandwidth, delta mu, is determined by the generation process. Okay, this is determined by the geometry plus the generation process. Okay, so this is very complicated. All right, so usually we'll just work with whatever is given. But this can be further, we can experimentally, we can use pinholes, 2 pinholes to collimate the beam to try to reach a controllable transverse coherence width. Anyway, that's beyond the scope of this lecture. What I'm trying to say is that this is a very difficult parameter to control. Okay, but nevertheless, it is born with the laser. No, sorry, the beam is born with a parameter, and when you want to get interference from the beam, then the 2 sources needs to be within the coherence width length. Okay. All right. So that's pretty much the first point I want to cover today. I don't have time to go to correlation. I do want to save you some time for your experiment. So you see, I'm making an effort to improve. All right. So I think we just cut it out. Okay. We will have 2 simple quiz questions, and maybe the next lecture I will try to do correlation. Okay. Let's see how this will work out. All right. Yeah. All right. Cool. All right. Is it possible for LED light for 2 spatial and temporal overlapped beams? Okay, so that's my 2 questions. So since this is a yes or no question, I will just have yes and no. Okay. All right. So this is your time now. please come up. And we don't have many people, but try to stay in the line.
And first one, even partial interference counts, right?
Yes. We have 5. All votes for yes. Great. But let's still try to debate a little bit. Now, you 3 will debate together, and you 2 will debate together. Okay. So let's do 2-minute debate. Maybe justify your answer to the other person.
Calculation on the board, right? You would need to align it to like in the scale of 1 micron. So you have to be very precise. But
Yeah, it depends on the displacement distance of the beams.
Yeah, that's also good.
Or you can be a very good LED lens. Just a very good LED light with a very narrow bandwidth. Maybe. I would suggest
Use a color filter to
because even if lasers,
it should be possible.
it's a very coherent beam, it still has a coherence level in some way.
It's completely loose.
So we didn't get into the coherence level. Like how does it work? Right.
But for this course or
No, like when we talk about how to get like the
1 minute.
the LC, the L-theory, but we didn't know how to determine that. But there's a threshold, and they can produce it. There's a threshold, and they can produce it, but we don't know how to get this threshold.
All right, time's up. Get back to your line. And after this very heated debate, does anyone want to change position? Want to switch? No? Okay, everybody pretty certain that you got the right answer?
Probably.
Pretty certain?
yeah.
Okay. All right. The answer is yes, of course. So we have everyone. Okay, so Vida, Masfa, and Simon, and David, and Phoenix. Okay. Do I spell the all round? Oh gosh, always. It's a difficult.
It's a cool name.
Okay. All right. For next. All right. So good start, guys. So if you earn 2 rights, if you get both right, then you can get a point. Yeah? Isn't it exciting? All right. So second, is it possible for laser to completely lose interference fringes for 2 spatially and temporally overlap beams? I'm talking about like 2 laser beams going through an interferometer, right? And you just overlap them temporally and spatially. Of same laser, yes. Is it possible for it to completely lose interference fringes? Or even partially, it doesn't matter. Can you do anything to it to reduce its fringe visibility? That's what I'm trying to ask.
Are you going to do for the both beat at the same time, or only for one?
I'm not specifying that. You can use your imagination. I'm just saying, is it possible to do anything to this setup?
But you're not allowed to make one of the beams go a much longer way because they have to be spatially.
Yes. So
overlapping
given that they are spatially and temporally
Yeah.
overlapped,
Okay.
is there a way to kill the coherent, to kill the interference fringes?
Can you put a polarizer in between?
All right. So I'm not taking more questions. Okay. This is as far as we go. Now, please, this is the first round. Please, this is the real question. Okay, let's please stand by the answer that you think that's right. Okay. You can choose any answer because we're gonna do a debate. Do you always do you four agree yes and you will vote for no? This is called peer instruction, not peer pressure. Okay, so do not work under peer pressure. Use your logic. Everybody's for their own. If you're on the point, it's yours. Okay, so you're not bosons. You should be fermions in this case. All right. Do we have 3 yes and 2 no? Okay. If so, then I will have I will have you 2 debate and I'll have you 3 debate. Okay. 2 minutes.
You think it can use interference? What sort of thing can we do to make it use?
Yeah, I would say coherence net. Yes, whether they're the or recurrence thing. And distance is travel over distance difference they travel
And you still have to
over the
manipulate them very big.
just there's 2 equations to
Make it very large, but it's still
just simply a laser with
I was just thinking there's a lot of ways
even though
to
a
try to
laser
build
is
an
especially
interferometer, but it still doesn't work.
especially over that like
Yeah,
but we can still have a laser with
So
a little bit
spatially and
quite a
temporally,
bandwidth.
the name is
Let's use this computing.
or lab.
Mm.
If you make it like some Qs, it will not.
Okay.
be spatially temporal.
Sorry. Let me just not make this a very strong condition. Partially. Okay. Partially. I'm sorry.
I mean, I'm thinking like
Because partially include complete. So to even lose
if you
inference
have,
fringes at all.
like this is for example, you're looking at receiving strength. This one is very rough, like flat, like rough. So that maybe also make
No,
it not-
that doesn't make it lose it. That's
Yes,
make
you
us
don't see-
observe it,
yeah,
right?
don't observe it. Because the laser to
Those are like technical.
what if you do one of the beams has a polarizer like this, and one of the beams has a polarizer like this?
And that time it's spatially lost overlap, right?
Yeah, and also if you just place it in the same way.
If you do one, we do them 90 degrees apart. We will still interfere maybe. Yeah. Can the light, can it interact with each other if you have it 90 degrees apart from each other?
No, they can't. We can't polarize them because each beam has the same wave direction.
If you put a horizontal polarizer, there will no beam left.
But what if the laser is like
You
this?
put a 45. Yes.
Then
All
you
right.
have one polarizer
20 minutes.
and one polarizer like this. Go forward.
Excuse me. Sorry, Gita.
That ball will not. If it's circular or elliptical polarizer, if it's perpendicular polarizer, then I think you should have it exactly that polarizer.
Okay. All right. Time's up. Let's back to your line. Please move back to your line. If you want to switch, that's okay, but later. Were you here?
Yeah.
Were you were there, right? Move back to your line.
You can change like
No, but you can check.
No, not yet. Okay, if you want to change, do it now, please. If you want to switch your position, do it now. If you feel like you're convinced of the other answer, you're not so sure about your own answer, you want to change your position, do it now. Okay. All right, so you all go for yes. Yeah. All right. Now we'll have second round of debate, and in this round you will debate with them. Actually, no. You and him will debate.
We too?
Yeah.
Yes.
And you will debate with Phoenix. So Phoenix will.
We can change the polarization. So
It's just that he's very bad laser.
Yeah, I also said that, but then I guess technically it's not laser light, if the laser is really bad.
but will it still be spatially for all of them?
Yeah, I was saying like you could,
How would you change to
Yeah, I can
be?
like if you have a,
something.
polarization of light,
Yeah.
so
How
if you
would
have
you
light
change
that's
to identical
like
beams
polarized
in the
linearly
different
in this
ways?
direction, and when one of the beams you have a linearization is polarized like this, and the other beam is polarized like this, then they will not interact with each other when
But
they
if
get back, so we
two
will not be
ways
able
that are
to
going in is
interfere.
identical,
Yes.
how do you plan to
Also,
change
the
them?
polarization will change when they hit the
One
mirror.
hand I have a polarized circle.
Ah, that's
Yeah.
also right.
But
Yeah, so you
only
not necessarily
problem
need
is,
a
will it still
need
be
a
spatially
need a
coordinated?
you don't necessarily need a polarizer.
If
You can just have
split them up.
Yeah, you
Yeah,
just
not
have like
spatial.
a quarter wavelength take or whatever, quarter wavelength that make it circular, you postarize or whatever, and when you will maybe break the interference.
Mm-hmm.
Yeah, I even remember we did a lab at home, we used some
In a
apparatus
mirror.
which could,
And then it reflects. If two identical waves go in,
but that was
they will
amplitude
also be
modification,
identical
but that
when they
could
go.
also change the phase. That would not matter. Oh, really?
even though it's temporary overlap, like two lasers, like laser strand at the same time, it doesn't
So
mean the
this spatial and temporally overlap
the
condition is
two-
at the end also it
the
will be
two
overlap.
photons.
Yeah.
Yes.
And
leave
that's
at
what
the
I
same
mean.
time,
At
right?
the
So
end,
it still
at the
has some-
camera,
Yeah.
they are
Camera
spatially and
is-
temporally overlap.
Mm-hmm.
It still has some.
But how will you choose one of them if they are identical?
If one has different polarization, then that means it's not spatially overlap at the end, right?
I'm not answering that question.
Mm-hmm.
It was quite a strong stain.
You can ask your classmates if they think polarization will count as a misalignment in spatial. You can ask them.
Yeah, I don't think your argument about what's the word for it?
1 minute.
You have any
Så de
other
var
ideas?
påverkar faktiskt. Simon, vad påverkar faktiskt?
Affect.
I don't think you plan to how to affect the beams away is not correct. But I still think that
It's very strong
no
to
laser
say
is
no to
perfect,
this one
so
because
they
then
will
you say
have
there
a
is no way
finite
in the entire world
coherence
to
time
do this.
distance.
I think even if you're not entirely certain how you would do it, I still think more for you guys. Because I have a few ways that depending on how you define like the conditions, they could be valid.
Mhm.
You could maybe use polarization or a quarter wavelength to make it.
Like for the light, it is it's distance travel. For the LED light to produce interference, it is to make the distance travel smaller than
So
the
they are identical.
coherence time.
So very-
Yeah, can we somehow make the distance travel for photons of lasers be longer than their coherence length or coherence time?
So
I think
what comes in?
the problem is
This
then you
one
break
identical.
this
That's why
condition.
identicality.
Or
Then
maybe
come back,
I-
that it and produce twice.
Mm.
So these are always in same amplitude.
Then we break one.
1 minute.
But the spatially and temporary overlap doesn't mean the
Don't
same
think at
photons.
starting
Or,
there is no.
right?
Yeah, so you say the laser has infinite
No.
coherence distance in time.
Not completely sure,
I think yes.
Okay.
actually.
Yeah, because So does it just is 1 frequency and 1 laser and the how does it and the coherence then is infinite?
It's not infinite, but
If it's not infinite, it's possible, right?
All right, thumbs up.
yeah.
Okay, go back to your line, whatever it is. Okay, anybody want to switch position?
One brave.
Anyone? Anyone else? After this 2 rounds of heated debate, anyone want to switch position? 3, 2, 1. All right, no more chances. Answer is yes. Yeah, and the key is polarization, correct. And actually the same thing within the LED light will never be able to achieve perfect like visibility 1 interference fringes because LED is randomly polarized. Every photon is randomly polarized. So there's always, you know, this and this photon. And when we earlier when we're calculating the interaction term, right? It's supposed to be a product of a dot product between the fields. And this has to do with the polarization. If polarization is vertical, perpendicular to each other, then of course this interaction term will be 0. It will directly turn off the interaction. Yeah. So for this round, we have Rita, Simon, David, and Phoenix. All right, cool. Good job, guys. Fun, huh? All right, cool. When you do the optics experiments, one of the lab is to do this. Yeah, to control the polarization of beam at each arm and to kill the interference fringes. It does not mean it lose coherence. Okay, be very careful. Even though you don't see interference fringes, that's why I'm not phrasing this to lose coherence. I'm phrasing this as lose interference fringes. It's not the same thing as losing coherence. Got it? Yes.
If you divide a beam and do the polarization,
Yeah.
it's still spatially overlapped.
Yeah, it is.
Even if you divide it.
When I say overlap, it means they are overlapping at the end at the camera.
Oh, okay.
And when you change the polarization of one arm, it doesn't change the trajectory of the beam, right? Yeah, so they will still remain spatially and temporally overlapped. And the coherence length and the coherence time will not be altered by the polarization. So all the coherence property are kept intact, but nevertheless, your interference fringes can still be lost for other reasons. Okay, so you need to be careful. Interference fringes, that does not 100% reflect the truth about your coherence. It's just a way, it's like a necessary condition. If you don't have no coherence, you don't have interference fringes. But if you don't have interference fringes, does that mean you don't have coherence? No, it doesn't work both ways. Yeah, so that's the logic. Right, we need to be careful there. All right, cool. Thank you very much. I'll record this. Congratulations on 4 of you. All right, so let's move to the lab. I will join you shortly.
So how will be the group be? Same as
All right.
So you will be working with David in the spin lab, and Tom will join Phoenix. Tom is sick today, so he's not showing up. But if Phoenix stays, so she has up to midnight to decide. Okay, and so are you guys. So if you decide by midnight, if you decide to drop out, that's just send me an email. Let me know. Then I will rearrange the group. That's no problem. Okay. But as it is now, we will have Tom working with Phoenix on the optics, and you two will be together on spin, and you and David will be on spin. Okay.